My name's Dumitriu, and I'm the artist of Engineered Antibody in the exhibition Under a Viral Shadow. And this is the work. It's based on an engineered antibody. It was a project that I made at University of California, Irvine, when I was embedded in the Liu Lab for Synthetic Evolution there. And they're working with non-canonical amino acids, so they're working with putting more amino acids into a living thing. Basically, everything in the world that's made out of protein, meat, hair, anything, is made of a combination of 20 amino acids. There are 64 in total, but no normal living thing has more than 20 amino acids in it. But they're working, can you put 21 amino acids in? Can you put 22 amino acids? Can you put 23 amino acids? And this gives them the option to kind of look for things like antibodies with a much greater range of options. So they could have the possibility to, solve a disease outbreak or something by having this much wider range of options. So the scientist I was working with, Chang Liu, was looking at an antibody which was originally isolated from the blood of an HIV positive patient, but in this case, he'd made it so it had 21 amino acids instead of the normal 20 amino acid signature. And the sequence of it was 452 amino acids long. And what happens with these amino acids is, due to various reasons and things like physics, they fold. And when they fold, they form proteins. So these antibodies are essentially proteins with a light chain and a heavy chain protein structures. And when they talk about amino acids, they talk about this necklace metaphor, a string of beads over and over again. So I wanted to know, if I was actually going to make this string of beads, what would it look like? So this necklace is, it's made of 452 beads, so the 452 amino acids in the sequence. Each of the beads physically contains the amino acid in the sequence in its crystalline form, including sulfatyrosine, which was the amino acid that they'd added in to make it 21 amino acids. And then, so each of these beads are made of polymer clay, and the reason for that is some of the things that they were trying to find with using these synthetic biology kind of methodologies is new polymers. So I was thinking about polymer clay. It's mixed with the crystallized amino acid and then fired. So I hand made the beads, and then I strung them in the exact structure, exact order. And then it was after I got back from the lab, so early, because this is in about 2015, 2016, sort of an early Zoom call kind of method. It was a Skype call in those days, I think. We went through painstakingly the structure of the protein. So the necklace, the beaded necklace, was folded and looped and folded to make the exact protein structure in the engineered antibody. So Chang Liu, the head of the lab, confirmed to me that basically you could in fact reconstruct the antibody from the artwork. So you could extract the crystallized amino acids from the beads, and you've got the structure that you need to know to make the protein. So everything's in there. When I was going through this discussion with Chang Li, it became obvious to him that he'd made a mistake in what he thought was the looping structure as well. So he had to go back and change his model, which was a kind of interesting dialogue with having to kind of explain it to artists and how that all works. The background to it is dyed with Kumasi blue dye, which was originally a wool dye, but is used now in the lab to dye proteins and DNA and amino acids and things like that, because it binds very well to kind of biological stuff. And it's this bright blue, it's called Kumasi Brilliant Blue, and I worked a lot with that. And the background, the embroidery there, is based on one of these diagrams that they show you to explain what an antibody looks like. But it's it's so abstract, you can't, as an artist, as a normal person, as a lay person, non-scientist, who wants to actually know what they're really looking at, makes very little sense. So it's one of these kind of abstracted diagrams that scientists work with. So I kind of had to go beyond that. So I wanted to incorporate it in the layer. And then behind that, you've got linen, which I tend to use as a metaphor for biotechnology in a lot of my works, because linen was derived from a bacteriological process, a very complex biotechnological process in itself in very ancient times, in ancient Egypt. So I'm always reusing this theme of linen, and it reappears a lot. And the silks, alluding to Louis Pasteur's PhD thesis, which was on the diseases of silkworms. So kind of the history of microbiology is always in the work as well.